All right, we're going to continue moving through chapter 5, today looking at section 5.5, which deals with the substitution rule. So this is like our first special rule that we use for integrating certain types of functions. So the way I liken this, the substitution rule for integration is like the inverse process of chain rule for differentiation. So we use chain rule to differentiate composite functions. And when we were introduced to chain rule, like it allowed us to take the derivatives of much more complicated functions. Substitution rule for integration we typically use when looking at composite functions as well, which allows us to integrate much more complicated functions. But composite functions aren't the only types of functions that we can use the substitution rule with. So we're going to take a look at a lot of different examples just so you kind of get a feel for some of the different ways that you can integrate via substitution and some techniques that you have to use in order to use the substitution rule effectively. Okay, so we've got several examples to look at today, and it's not going to get us all the way through our lesson. I'm going to save a couple of examples for in class on Wednesday or Friday as well. All right, so the directions here say to evaluate the integral. For number 1, we have the integral of x plus 1 raised to the 5th power, which we are integrating with respect to x. Now, one of the ways I guess we could work through this is to like expand out x plus 1 raised to the 5th power using the binomial theorem, and then you could integrate that result term by term, but that's not very efficient when it comes to integrating this function. So we're going to take a look at how we can utilize the substitution rule to help us integrate. So again, when we look at this function here for number 1, we see that we have a composite function. So we have the function x plus 1, which we're raising to the 5th power. And typically, if we want to integrate this using substitution, we're going to let u equal the inner function in our composition. Okay, so the inner function in our composition is going to be x plus 1. Okay, so once we've done that, what we want to do next is we want to take the derivative of that equation. But rather than taking the derivative of the left-hand side as du over dx, what we're going to do instead is we're going to write that derivative in the form of a differential. Okay, so really, like what we're going to do is we're going to take the derivative of the right-hand side and then move dx to the right-hand side as well. So the derivative of x plus 1 is going to be 1, and then we're moving dx to the right-hand side, multiplying dx on both sides. Now, typically what you want to do here is isolate dx, but dx is already isolated for us. Okay? All right, so what we're going to do now is we're going to go back and rewrite this integral and hopefully get it written in terms of u and du only. So if you can write your integral in terms of u and du only, that's great. That means you've made the correct u substitution. If you can't, there are some times where you have to like do some algebraic manipulation. But if you can't get your integral written in terms of u and du only, you likely made the wrong substitution for u. Okay, so if I replace x plus 1 with u, we get u raised to the 5th power. And then we can replace dx with du. And like we said, we have our integral written in terms of u and du only, which is great. That's what we want. So we can now go ahead and take the antiderivative, which is u to the 6th power over 6 plus the constant c. But we're not done yet because our original function was not written in terms of u. It was written in terms of x, so we need to go back and replace u with x plus 1. So that's going to give us x plus 1 raised to the 6th power over 6 plus the constant c, which is a much more quick and efficient way to integrate composite functions. Okay, so what I'm going to recommend that you guys do here is like we've got a ton of examples to go through. I would try for at least maybe the first 9 or 10 questions. Try working these through on your own and see if you can work through the integral on your own. And then you can check at the end to see how I worked it through. When we get to some of the problems at the end, you're probably going to need to see me work them through to like have an idea of how to integrate functions of those types. Okay, so you can practice these on your own and then check at the end to see if your work matches mine. But I'm not going to tell you to like pause here and do it, pause here and do it. You guys are going to do that just on your own as you work through the lesson. Okay, so for 2, we're integrating the square root of 3x plus 5 with respect to x. Again, we have a composite function, so we're going to want to let u equal the inner function in the composition, 3x plus 5. And then we're going to differentiate both sides, writing it in the form of a differential. So that's going to make du equal to 3 times dx. And again, like I said, we want to isolate dx. So dx is going to be equal to du over 3. So our goal is to get our integral written in terms of u and du only. So this is going to become the square root of u. We're going to replace dx with du over 3. So I can pull 1/3 out front. Rad u is u to the 1/2 power. So that's going to be u to the 3/2 divided by 3/2, or 2/3 times u raised to the 3/2 power plus c. And then 1/3 times 2/3 is 2 over 9. We're going to go back and replace u with 3x plus 5 raised to the 3/2 power plus the constant c. Okay, so that right there would be the integral for number 2. All right, when we look at 3, a little more complicated here because we have the quotient of a function and a composite function. So again, typically with this, you want to let u equal the inner function in the composition, x cubed minus 8, which when we differentiate, we get du equal to 3x squared dx. And then we can replace, or when we isolate dx, we get dx equal to du over 3x squared, which is going to make this the integral of x squared over u to the 5th power. And then we can replace dx with du over 3x squared. And the good news is we get the factors of x squared to cancel. So we get our integral written in terms of u and du only. So I can pull 1/3 out front. The function 1 over u to the 5th power is u to the negative 5th power, which we're integrating with respect to u. And then that's going to be 1/3 antiderivative is u to the negative 4th over negative 4 plus c. And then I'm going to just pull the negative 4 out front, so that's negative 1/12. We're going to replace u with x cubed minus 8 to the negative 4th power plus the constant c. All right, and that right there would be the antiderivative of that function. When we look at 4, we have the product of a function and a composite function. So again, we typically want to let u equal the inner function in the composition. So we're going to have that equal x cubed, which makes du equal to 3x squared dx. And when we isolate dx, we get du over 3x squared. So again, my goal is to get this integral written in terms of u and du only. So we get the integral of 2x squared times the cosine of, we replace x cubed with u, we replace dx with du over 3x squared. The x squareds cancel, so we get our integral written in terms of u and du like we want. So this is 2/3 times the integral of the cosine of u, which we're integrating with respect to u. And then the antiderivative of cosine is the sine of u plus c. And then we can go back and replace u with x cubed. So this is 2/3 times the sine of x cubed plus the constant c. All right, for 5, we have the integral of 3 times the secant squared of x times the square root of the tangent of x, which we're integrating with respect to x. So this one's a little bit more difficult in that, like, we have 2 composite functions here. So we want to make the correct substitution for u that hopefully gets our integral written in terms of u and du only. So the u substitution you want to make with this one here is tangent. And the reason we want to let u equal tangent is when I differentiate tangent, the derivative of tangent is secant squared, which means I'll be able to cancel those secant squared factors. So we get dx equal to du over secant squared. And then this integral here becomes the integral of 3 times secant squared times the square root of u. We're going to replace dx with du over the secant squared of x, so the secant squareds cancel. And then I can pull 3 out front, and this is 3 times the integral of rad u du, which rad u is u to the 1/2 power. So the antiderivative of that is u to the 3/2 over 3/2 plus c. Dividing by 3/2 is the same thing as multiplying by 2/3. So 2/3 times 3 is 2. We're going to replace u with tangent. So that's going to be 2 times the tangent of x raised to the 3/2 power plus the constant c. All right, for 6, we have the integral of x cubed times 5 raised to the x to the 4th power, which we're integrating with respect to x. So again, we have a function times a composite function. We're going to let u equal the inner function in the composition. So that's x to the 4th. du is going to be equal to 4x cubed dx, which makes dx equal to du over 4x cubed. So this is going to become the integral of x cubed times 5 to the u power, and then we're going to replace dx with du over 4x cubed. So the x cubes are going to cancel. I can pull 1/4 out front, and then we're integrating 5 to the u power with respect to u. And again, we have our integral written in terms of u and du only, which is what we want. So we can go ahead now and take the integral of 5 to the u power, which is 5 to the u power, over the natural log of 5, plus our constant c. And then lastly, we're going to go back and replace u with x to the 4th power. So that's 1 over 4 times the natural log of 5 times 5 to the x to the 4th power plus the constant c. All right, so we're going to continue with some additional examples in the next video.